any question? No one across them. Is our internet up?
So you check if you can check the density of the Earth by comparing the average to the surface, right? And that's how you know if there's a cavity inside or not, because then the surface density would be higher than the average density.
No.
No, that's what I can.
I think you cannot.
Oh.
Just by measuring your G. Is that the point?
Oh,
what did you say?
Oh, I can't. So I was thinking more of how you could tell if there was a hollow, like a hole in the center or something. And that would just be if you measured the density on the surface, then if it was greater than the average density, if you took the mass of the Earth, which you'd have to calculate with the formula already.
Yeah. Decent, yeah. But then one could argue that, okay, maybe it's all outer layer and there is a inner layer which is very dense. And then there is the average is sort out. You might not get it completely going. How it is done is using earthquake. The earthquake creates waves, and there are two waves it creates. One is longitudinal and one is transverse, and they go at different velocities in a medium. And if you're on the other side and you receive these waves, then you can tell what is the density. You can pretty much, it's like scattering problem. You can reconstruct what could be there.
So you measure like the complete opposite side of Earth. So
yeah, it could be anywhere actually. So that's true. So for example, this is Earth, and let's say this is dense, this is not dense, this is less dense. So this could be here, and you receive the wave somewhere here. And this usually is a spherical wave like this. And the way this will go, there are two waves it has. One goes in a certain way, the other goes in a certain way. And the difference between the amount of time it takes. But don't go by the time at all, just go by, there is a structure, this wave can sense that. And based on what you receive here, or if you have more detectors, that's great. Then you can tell a lot. Like more the detection, pretty much like a scattering problem. You have everything and you can sense about what is there inside. So, yeah, that's what an earthquake sensor has information about. Look up longitudinal and transverse waves in an earthquake. I think that's a good search for it. Curtis. Curtis, is the internet good? Seems like it's only you.
Yeah, I can see the board.
Okay, good. Yeah.
Okay, so we technically haven't proven that there's something inside the Earth.
Yeah, and this is how we know. Like I think, there might be other ways, but one of the primary ways how you will get the information about Earth core is using this. Is using earthquakes. And this becomes a challenge, especially if you're thinking about other planets. Here, at least you have earthquake. Now, if you're on Jupiter and you want to know how is Jupiter's content, is it metallic inside? Is it how much of the radius is metallic? Like remember, Jupiter is gaseous. A good bit is pretty much gas or dense gas. So the obvious question to ask is how far is that gas? After how long does it get really hard material, and how far is it metallic? These are very reasonable questions to ask, but you're pretty much helpless there. You just look at it and get, unless you send a satellite, and that too, satellite, what can it measure? Usually it can measure gravitational field. But earthquakes are the good ones. So there you would like to have to do something on the other side and then measure it that way. We're getting better at it, but we don't have so much money that we can actually send things and have an explosion there which can be sensed on the other side. It's sort of too big challenge to take up. So I think these are still open questions as to if one can come up with smart ways. Usually they're just smart. I would stress on that sometimes if you just think differently, you might have people might have missed something that was possible, like even with current technology. So can you measure the distribution of mass in planets? How would you do that? Forget about galaxies and other things, that's more challenging. But let's talk about planets. So I think these are reasonable questions that are asked generally. Like another thing is magnetic field of Jupiter. Right? How can we do it? Of course, you can. These days, how you measure magnetic field is you go there with a spacecraft and measure these things. But can you measure it sitting on Earth? Right? Because Jupiter has a strong enough magnetic field. Can you do something cheap without spending enough money? Can you be clever and get something informative about it? Those are the nice questions one can ask. So, yeah. And that's about the comment.
Yeah, pretty much.
Yeah. And there was another question that came up last time. Christian, you asked the mass, like the CERN. Why, if you, I mean, the question was that you have a proton. Like if you, the simple understanding, the way I portrayed it, this is a proton. And if you have a proton, that makes sense that same size, that this has to repel. But if you have an electron, why do you need so much energy, right? And because I was motivating everything in terms of attraction, repulsion, that made sense. But the point is, why you need so much energy is not because of the repulsion. You need so much energy so that when they come together, when this really bombards each other, the idea is to create new things. And to create something, you need energy. So the simple idea is E is equal to mc squared. Like let us say you come and bombard these things, usually create particle like top particle. Top is the name of a particle. Right? That's one of the massive particles if you want, or Higgs, let's say. If Higgs is not usually found, like Higgs is popular, right? These days we all talk about Higgs. So if you want to create a Higgs particle, you need to know its mass. You need to have that much energy. Mass times in kgs multiplied by c squared. You need to provide that much energy. And that's the whole goal of this. Have so much of kinetic energy that whenever this happens, there is room for creation of this. And that's a very small room, by the way. That's a statistically very small window, but that's the game you play. So you come up with so much of kinetic energy that when you really get hit, chance that you will create that. So that's why, and whether you're an electron or proton, you need that energy. That's a kind of energy. So I should have, I guess, I was thinking in terms of attraction repulsion, and it made sense of why.
Yeah, I guess I just assumed that we were still measuring the same electrons and how they got scattered.
Yeah, I think I motivated it in that sense because I think the way the story went, it seemed like, oh, why not? I was also thinking. Yeah. Good questions, yeah. So, and I'll bring up, since we are doing the mass and since we cannot experience anything inside, I think there is a similar thing that's going on. If you look up the dark matter issue, that's pretty much very related, and I'll try to motivate it. Maybe I'll try. Let's see how far it goes. Maybe there's a connection of how nucleus was invented or discovered. So the same argument can be used for dark matter. Like it's the same question at least. So I'll motivate it. So let's proceed and let's do it. It's all related sort of. Okay. Curtis, we have Matt also now. Yeah, good. Okay. I was worried that we were losing everyone on the virtual people. Okay, so homework 4 was due today. Oh, is it because of homework 4 is due? I noticed that whenever the homeworks are due, the number of students goes down a little. So, sorry. September 3rd. So, 5. September 11. And remember that I said if you submit it early, I can grade it before the exams, especially if you send me an email. I really like it to be graded. I'll surely do that. So that's the way to put it. And yeah, there's a preview of midterm 1 uploaded. That's a challenge question in a sense, but midterm 1 September 11. Right. Yeah, that's something I have to ask, right? But there is no one here. So Matt and Curtis, are you in Carbondale?
No, I'm in Carterville.
Matt, you're in Carbondale. Curtis, are you in Carbondale?
Yeah, I am.
You are, okay. Do you guys get out of your house once in a while for shopping and all? Or do you
Yeah,
stay?
every so often, yeah.
So for the midterm exam, you can come to the class and take it?
Yeah, I mean, I'll come.
Do you feel uncomfortable about it?
I mean, ever so slightly. I know some of the students at SIU, nobody in the class, but there are some students at SIU that I'm really worried about, but I'll come in. I already have a lab that I have in class anyways, so it's not that big a deal.
So how about this? I can give an option. If you guys can make a system camera or something, that's your responsibility, and convince everyone in the classroom that you're indeed perfectly, everything is being fair, then you don't have to come. So if there is a discomfort there, okay? Is that clear what I said?
Yeah.
So if you can make a camera system point to your, I'm not saying where and other things because that gets very quickly, I don't want to make the rules. You have to convince everyone around. Imagine that you're convincing your peers that we have been fair and taking a proper test, correct?
Okay.
Okay. Okay. But if you are in Carbondale and if you have been getting out here and there, then this is if you feel that's the word you said, this uncomfortable. So you want to be careful.
I'll come in for the exam, but I like to keep what I'm going out to a minimum.
Yeah. So
just to be safe.
Yeah, let me know if there is anything extra discomfort you have about the exam. Okay.
All right. Sounds good.
Because the number of cases are increasing from what I know in the campus.
Yeah.
Be careful about that. Okay. Okay. So anyway, I think on Monday we'll talk more on that when others are also there. Curtis, have you been? Yeah. Is that the discussion was clear? So we'll bring this up again on Monday. So have some think about it meanwhile. Maybe this is too much on the spot. Okay.
Alrighty.
Yeah. Okay, so we talked about Gauss's law, the integral form. Basically, it says that surface integral of the electric field is equal to, so this is having an R dependence in there in general, that's equal to the charge Q enclosed over epsilon naught. So let's talk about a solid sphere. Let's talk about a hollow shell first. So let's say hollow shell, is that spelling correct? Hollow? edge, hollow shell, and let's say there's a charge Q put on it on the surface, right? And there is a charge Q on that surface. So notice it's really a shell, like it's a spherical shell. Let me put that spherical thing down. Right? Spherical shell, and again we use symmetry considerations. It's important that we go ahead and say that electric field is actually radially outward. That's a requirement in this situation. So assumptions or symmetry arguments is more than assumption. Based on symmetry, one requires that electric field, which could have been having r theta phi, is basically radially outward. The direction is in the radial direction, and E of r. The magnitude is simply dependent on r. So this is uniformly charged, right? That's the basis on which you do this. Uniformly charged. Right, if that is the case, and again we ask what is the electric field everywhere, what is the electric field outside, what is the electric field inside. So let's again ask, make a Gaussian shell, right? So that's a sphere. So this is a Gaussian sphere, Gaussian surface, let's say, Gaussian surface. And on that, let's do dA. So this is that surface S that we talked about. So this is that surface. Let's say its radius is r, small r. And the radius of the shell itself is capital R. So dA dotted with electric field, we said is R times E of R. And since we are going to be on the surface, this electric field, so this integral is always on the surface of the sphere, that will be always R. That's equal to how much charge is enclosed if this sphere, as I've drawn it, it's outside that. So it will capture all the charge, right? Total charge is Q. So that's just Q over epsilon naught. Right, that's a straightforward relation. Then dA here is the normal to the surface, that's r hat. So this is E of r comes out. Why does this come out? Because everywhere on the surface, its magnitude is the same. Right? There is no angular dependence in this electric field. And if there was theta phi in there, then you would say, oh, there is more electric field here, then that would spoil the spherical symmetry. Then due to spherical symmetry, this is angle dependent, and this integrals are on the angle. So it comes out, and what you have is this integral of dA, but dA has a normal direction in the r hat direction, dotted with r hat itself. And that's equal to 1. This is the same argument that went through for a point charge. So that tells you that E of R is equal to Q over area is 4 pi r squared. So I write that as 4 pi epsilon naught and r squared. Is that visible? Oh, guys. No, the wrong camera. You guys need to tell me, sorry. Curtis, Matt?
Yeah, I thought you were writing, but I wasn't sure, and I just didn't say anything.
Yeah, sorry. Yeah, you guys missed everything. Yeah, okay, for the last 5 minutes. Okay. So the point was I was talking about a hollow shell. And so this is the shell with the charge Q on it, correct? And there's electric field coming off from it. This is a Gaussian surface. And I assume that the electric field is R hat times the electric field magnitude. And you use the same idea that we did in the last time for point charge. And we show that the electric field is Q over 4 pi epsilon over R squared. And is that visible, the last sentence? Sort of, maybe?
Yeah, I think so.
There you go. Okay, so that's good enough. But what about the electric field inside? So this is for R greater than, so this is capital R being less than R. What if the observation point was inside the surface of the hollow shell? And then you would again ask the same question. Let's say positive charge here. This time have the surface inside. That's your Gaussian surface. This is again capital R, but this is now smaller. Small r is less than. I don't know what's the electric field inside a shell, right? And what will be the electric field inside the shell? Any guesses? The electric field is like a point charge outside. What about here? So it will be 0, correct? And that should come out using the Gauss's law. Again, we do the same idea. So this remains the same. dA R hat dotted with R hat times electric field E of R. That's equal to, that is no charge enclosed in there. Right? So this is equal to 0. So this says that E of R times that's equal to 1. This is 4 pi R squared. The area, that's equal to 0. Area is not 0, so electric field has to be 0. Okay. So we conclude that the electric field of a hollow shell is 1 over 4 pi epsilon naught. You can say Q over 4 pi epsilon naught. 1 over R squared. Maybe I should write the R equal to 0. So this is equal to 0 if R is less than R. And this is equal to Q over 4 pi epsilon naught. 1 over R squared if it was greater than. This is the magnitude. We already assumed that it is radially outward. So if you want to derive the direction, that's R hat. That's your electric field. If I were to plot this as a function of R, the magnitude alone, not the direction, then that is a radius R. So at the radius R here, it is actually, so this point here is Q over 4 pi epsilon naught over 1 over R square, capital R square here, right at that point. That's the maximum value you can take. And then it goes down like 1 over R square. It goes like this. This is 1 over R square. Is that clear? Right. It dips very quickly. And for less than R, this is 0. It is 0. So you're not confused there. So that's the line I removed. So it is 0 inside. Like exactly 0 inside the sphere. Okay, any questions there? Any doubts? Comments? And now let's ask the same thing for a solid sphere. And this should be thought of as an atom. Okay? So think of before 1896, people did not know that atom has a nucleus and an electron going around that. It was only very recently, that is 1896, or not even 1896 actually, 1910. 1910 is when they realized that atom has a nucleus and there is a going around, there's an electron going around it. There was no other way other than for it to go around it. So before that, the model was, so this was an atom. So there's a sphere, there was some positive charges and negative charges. They were all static, 4 and 4. Like, that was called a plum pudding model. Plum pudding means it was kind of a pudding kind of thing, and then there are protons sitting there like a, is that a familiar thing? Plum pudding? Right? Okay, so it's a plum pudding model. And the radius was atom. This is the R. This was 10 raised to minus 10 meters. Okay. This was all good. There was no problem. But then Rutherford performed this experiment where they came in with another proton, basically a helium atom, an alpha particle, and they bombarded it, pretty much what we discussed about CERN. And they realized that, oh, there is a lot of difference between them. And that's what we want to analyze. Okay? So let's think of this as so the idea is that it's very easily possible to ionize an atom. Right? Heat it up and it ionizes. It's very easy. Usually you don't work with one atom. You typically work with either a beam, which has a lot of atoms, or with a gas of atoms. So you take a gas and heat it up. All the electrons are formed because they start moving around, they start colliding with each other. So all these electrons, it's very easy they realize that it's very easy to ionize an atom. Even now we do that all the time, right? So it's very easy to ionize an atom, so that's positive charges. But then the question was, how are these positive charges distributed in this sphere? And we will address a simple question that what is the radius of the sphere? That's what we want to ask. Like we have an atom, how do you know that what's the radius of the sphere? That's the question. Let's ask that ourselves. How would we go ahead and figure out? Is there an experiment we can suggest or something? What's the radius of an atom? As of now, we know that the radius of this positive charges, what is the radius of the positive charges? This will be the nucleus, right? So this is, as of now, this is 10 raised to minus 15 meters. Right? Until 1910, it was considered to be 10 raised to minus 10. So what changed that they had to suddenly change from 10 raised to minus 10 to 10 raised to minus 15? This is a huge difference. It's like saying the whole solar system, or at least the radius is until Earth versus until Mercury. Right? Our distance from the sun is 10 raised to 11 meters. So I don't know the radius of the sun itself, so I cannot know. So that should be comparison. But this 10 raised to 5th is huge. So that's what we want to keep in mind. But so the goal is, what is the radius of an atom? That's what we write this. Using Gauss's law, can we tell something? And apparently, yes. So let's say there is a solid sphere now. This is the, think of it as a proton, and it has a radius r. Again, do the same idea, right? We wanted to find what is the electric field. First, we will do outside, correct? So outside idea remains exactly the same. Electric field is all radially outward. Right? Do the same thing everywhere. So outside, story remains the same. Outside is dA times r hat, dotted with r hat. Like we are assuming that electric field is radial everywhere, and that's E of R. Magnitude of R is equal to, what is the charge enclosed? That's Q. That could be the charge of a proton. I have shown this as a lot of positive charges, but if it's a proton, that's just one charge. So that's Q over epsilon naught. This is equal to 1. This can come out because everywhere on the sphere is the same, and that's 4 pi r squared. So you immediately say that E of R is equal to Q over 4 pi epsilon naught times 1 over r squared. So for a point charge, it is this. For a shell, it is this. For a solid sphere, it is this. Like, you cannot differentiate anything. And that itself gives you an idea. The point charge has the same form. Radius r has the same form. So apparently this does not have any information about this radius r. So by calculating electric field outside, I can get no information of the radius r. Like having a satellite outside Jupiter, you don't know where that gaseous part of that ends and the solid, real solid part of Jupiter begins. So those are all good questions. And inside, now we want to talk about inside, right? This is a good point. So now inside might have a point. So what is the electric field inside? So for that, we remove this Gaussian radius inside. Right? That's inside now, and that's radius r. Again, we say that it's radially outward electric field. Again, that has to do with symmetry. And now you do the same story. So this is dA r hat dotted with r hat E of r, right? And that's equal to charge enclosed now, right? How much charge is enclosed? How much charge is enclosed inside of this small sphere? Right? So we said it's a uniformly charged sphere. That's an assumption we are making all through. So if you know the volume of that, that might have a point. So let's say Q enclosed, because charge density is the same, right? Q enclosed divided by 4 by 3 pi small r cube. So that's charge density. Charge density is the same. Is uniform. That means to say that I can take any volume out of this and calculate this, it will be the same. So this will be the same as the total, which is capital Q over 4 by 3 pi r cube. Why is it the same? Because the charge density is the same. I can take any volume and get that argument going, right? But that gives me an idea of Q enclosed. Now I can substitute this to cancel out. Pi cancels out. So Q enclosed actually is equal to Q itself, and it is R over R cube, right? That's clear. It depends on the volume, so it is a scaled by, if I reduce the radius half, then the charge on it reduces by 1/8. This we learned in volume dependence in here. But that tells a lot of information in here. So this is equal to Q over epsilon naught times R cube over R cube. Right? Clear? The left-hand side argument goes the same. This is constant everywhere on this surface. Comes out. U of R comes out of the integral. This is equal to 1, and the surface area is 4 pi r squared. That remains the same. And this is important that this is a small r, like the smaller radius is coming in there. This is slightly different from what we have here. And the interesting part is that the radius on the left-hand side, right-hand side cancel out. Right? 3 of them go away. So if I were to rewrite this, this is the same as electric field is equal to Q over 4 pi epsilon naught. And now this is R over R cube. That's a constant. and R that is changing, that's in the numerator, is linear. Especially if I'm right at the center, what is the electric field? 0, because R is 0. But as I go out, this starts increasing. Until I reach the radius R, it keeps increasing. And from that point on, it starts decreasing. That's your electric field. So let me plot that, write that down clearly. So that's equal to Q over 4 pi epsilon naught. It linearly increases, that's R over R cubed, for R less than R. And it is Q over 4 pi epsilon naught, 1 over R squared. There's a direction also, R hat if you want, for R less than R. Okay. And how will this look like if I were to plot this? Clear? Any questions?
It increases until
Yes, it increases and then decreases, right? Question?
No.
Yeah. Okay, so let me plot this. Yes, that's correct. This is equal to, this is radius R, there is a capital R. So that's the maximum value. So the outside it stays the same. No difference between this and that. Right? But inside now does not come to 0, instead it gradually increases. And that is Q over 4 pi epsilon naught, 1 over R squared, exactly at that boundary. That's okay. Is that very clear? That is how the electric field for a proton is. Okay. Now this is 10 raised to, this we would at least until 1910, this was expected to be 10 raised to minus 10 meters. Okay. So what would happen? So now let's imagine what will happen if you were, so this is the radius I'm going, this is the radius, this is the proton, like there's an atom, you're pretending that is focusing on an atom. And now let's say that there is another atom which is really big, usually, no, what do we do? No, what was done was, yeah, so this was not a hydrogen atom, so they had this many things. So this was a gold atom, gold nucleus. Nucleus because you heat the gold and get rid of all the positive charges. Right? You have no positive charges left, so it's a pure nucleus of the gold. I think that's what they did. Or no, it had negative charges also on it, but it was the beam had actually only, it was an alpha beam, so it was only 2 helium. Right? This is a helium nucleus. And so they came up with this, and it's not that they have one atom, they never have one atom, it's a beam. Right? So there's lots of them, bunch of them. So think of this as a beam of atoms coming, and this is not one atom, they have a gold foil. Take a simple metallic foil, make it very thin, right? And you have a gold foil. So experiment, what it is doing is that it has a foil, right? Because you don't have so much, it's too much money to look into an atom, right? That one atom level. And you have a beam of protons or helium atoms coming through. But what we do know is, what is the information now that is available? We know the kinetic energy of this. So kinetic energy of each atom in this beam is known. Okay. And how do we know that? Because there are various ways to do that, right? In introductory level physics, you learn this, that if you have a let's say a positive and negative charge coming out, so this is the negative charge, and if you have a beam going through it, actually not even that, right? There's better ways of doing it. Put a magnetic field, right? Put a magnetic field in this, and if you were to have a beam of charges coming in, there will be, and this is a material, let's say, because they will, the magnetic charge will try to bend this, so let's say this is positively charged, so magnetic field is going in, what do you say, so this is positive, so this will bend right here like this. Is that clear what I'm saying? Right? All the charges will bend because of the magnetic field, so that will actually create all these positive charges here, and that will create an electric field. And then the magnetic field and or the magnetic force and the electric force balance out. Right? Based on that, force of the magnetic force is equal to force of the electric field that is induced. And after that, this will go just smooth. So there is a very specific choice of the magnetic field for which this beam will go through smoothly. So that's called a velocity selector. That means to say that you can measure the velocity of this. Remember again, atoms are too small, you cannot look at it. But still you can tell what is its velocity. Velocity means you know the kinetic energy. Is that clear? So the basic idea is that it is very easy to measure the kinetic energy of a beam. I didn't go through in detail. Should I go through in detail?
So that's like is it the Hall effect? Is it the same idea?
Well, it's the idea is the Hall effect, but it's not. This is called a velocity selector. Hall effect is exactly the same when you create positive and negative value. That's correct. But Hall effect would be when you talk about this how much electric field is created. That's Hall effect. But here you're using the Hall effect to measure the velocity. So the idea is there is magnetic field, so it is Q. Oops. So it is force of the magnetic field has to equal to the force of the induced electric field. So it is Q times V times B. Right? That's the force of the magnetic field. Right? It is QV cross B, but I'm saying it's perpendicular. And from the electric field, it is Q times electric field. Charge cancels out, so I can select my velocity. I have a system like this, and I will wait and see here how many charges comes in. That will be only for a very specific magnetic field will this beam come out. Otherwise, it will get destroyed in here or this. If the magnetic field is too large, it will go in that side. This small, it will come in this side, so you won't be able to get it. So that's called a velocity selector, but idea is the same. It's a magnetic Hall effect, right? So you can measure the kinetic energy. Now you have a kinetic energy coming in, so kinetic energy is fixed, and this is a peak, right? With a given kinetic energy, how far can you get to a positive charge? So this is positive charge, right? They don't like to be close to each other. How far can this reach then? If you have lots of kinetic energy, so that is half mv square, the maximum it can reach is when the potential is repelling each other, right? So this is Q1, Q2, 1 over 4 pi epsilon naught, Q1, Q2 over how far? There is a specific critical radius, right? RC. There's a maximum, that's it. If you have or let me ask, how much kinetic energy should I have to reach the surface? Is that clear? So for example, if you just have, if you have too little charge, it will come here, go back. Increase its velocity, it will come here, go back. But there is a very critical velocity when it will touch the surface. Now you ask, what if I increase that velocity? Then it will going to hit the charge, it will go deep into it. And the point was, if you say that it is 10 raised to minus 10, in 1910, Rutherford realized that they have sufficient energy to actually penetrate this and come out. They have so much energy, that means to say energy is dependent on electric field, right? That's here. That's really tiny. Right? They had energy somewhere here. So they expected this to go through. They expected to break open the, like basically break apart the nucleus. Instead, what happened is that in this experiment, when they bombarded it, instead of going in, they all came back. Not all, many of it came back. Like, it was not expected that it will come back. It should all penetrate, right? It's like saying, if you shoot, I mean, this is the language of Rutherford. He said that if I shoot a sheet of paper with a bullet, I don't expect the bullet to come back and hit me. It should tear off the paper. But that was a surprise he had. Instead of this tearing the atom, it came back. Very few of them because they were very small. Right? They were very small, concentrated. So it came back. So how did he explain this? The only way he could explain this is this R is not here. This is somewhere here. This is somewhere here, R, and this is 10 raised to minus 15. What happens in that case is this has to keep increasing then. Right? This 1 over R square has to keep increasing, and this is somewhere here. If I can draw that. Does that make sense? Let me draw that again here. So the point is, if the radius is small, electric field can be very large. That's 1 over R square. It will keep going if it was allowed to. But now this is another radius. Is that clear? So this is R1. That's another possibility, R2. If it was R1, the maximum electric field it can experience is this. If it was R2, the maximum electric field it can experience is this. And since, based on this experiment, it came back, the only way it could have happened is that it had so much energy. And based on the amount of kinetic energy he had, he could say that it is at least smaller than 10 raised to minus 15 meters, at least at that time. But now we know that it is 10 raised to minus 15 meters. And once you say that, oh, the protons are really small, then where do you fit in the electrons? So the electrons have to sit in there. Right? But electrons could have just sat there, right? But that's not okay because electrons will just collapse into it. The only way you can have a stable electron sit there is that it has to go in circles. Like Earth goes around the circle. Like if Earth were static, it is not stable. Like it would just fall into it. The only way it could be static is that, or stable, is that it has to go around the proton. And that gave a new challenge. What's the new challenge? What's wrong with electron going around the proton? It will have a magnetic field, that's correct, but more importantly, this cannot be stable. So what happens is that electron is going in a circle, that means it's accelerating. And an accelerating charge has to radiate. Like all accelerating charge radiates energy. So that means to say that if it radiates energy, this will lose energy, so this should collapse in that. Right? So that's not a stable atom. So Rutherford gave a great example of model, but that's not stable. And that raised a new question, and this cannot be answered in classical physics. This question, remember this was done in 1910, right? 1910 is when Rutherford gave this model, and quantum mechanics came in 1930. The first version of quantum mechanics by Bohr came in 1930. That was to answer this. But it was pretty much ad hoc. What Bohr said is that this just cannot happen. So instead of explaining it, we had to change our physics completely. That's called quantum mechanics. And the way in quantum mechanics, that is a way to look at it, but that's mostly uncertainty principle. But in very simple terms, you restrict this from happening. You cannot go beyond a certain radius. That's a way to say. And we'll probably you will see this in quantum mechanics somewhere else, and we can talk about that later. But very quickly, in 1 minute, let me give a similar problem, because I know I'm already 50 there, but in 1 minute, if I were to motivate you guys. So notice, there is a similar problem which is called the dark matter problem, which is going on today. Right? And that is and this is where you guys, this is an open problem even today. So this is where you should start thinking. Right? You guys are young. You should think out of the box. So think of a galaxy. Let's make it simple. Let's say it's disk-like galaxy. This galaxy. And that contains a lot of stars, right? And stars move around in circles. So there's one star there. They all have velocity v, right? So they're all going in circles. That's clear. The velocity of this is decided by g m1 m2 over r squared is equal to half mv squared. m1 m2 over r, right? Gravitational potential, or let's say r squared is mv squared over r. So let's say m1. So where m2 is all the mass inside the sphere, right? What is the gravitational force on a star that is somewhere inside? It is only the inside part that contributes. Outside doesn't contribute. Same argument as here, right? It is only the inside that contributes. So if you were to plot velocity of these stars as a function of r, velocity of the stars as a function of r, it is expected that it will linearly increase and then it will decrease. So that is what is expected. Okay? So especially the outer stars is the important part. So this is theoretical. But it is very easy to measure the velocity of the stars in a galaxy. In fact, even in an outside galaxy, these days we have enough resolution to actually measure the velocity, the relative velocity of these stars. But it turns out it doesn't obey this. It will go pretty much exactly here, but this is how the data looks like. They're all above. Okay. And so you say that if it has to have so much velocity, it must be, there must be mass somewhere, right? If the velocity is large, there must be mass. That missing mass is what is called the dark matter. And this turns out to be the case in every other galaxy, or every galaxy that you look around. The outer stars are going faster than they should using Newtonian physics. So there's something we are missing in our theory. Is that clear? So the suggestion is that if you go by this model, why can't we do this? We will actually extend this. Right? Our star galaxy radius is not this. This is actually, this is the radius. Right? This is R1, that's the radius R2. And let's say this is, if you were to now, and somehow, or how do you put this? Yeah, I should have started from here and then gone there. So the idea is that if you were to, so this is what is called, so this much, since we don't see it, that is, so let me put this like this. So there is matter here, outside part of the galaxy, which is called the dark matter. So there is matter here, but we don't see it. So it takes it all the way up and then reduces it like this. This curve has gone down, right? And then you say that, oh, that is why you see dark matter. And then you can explain it to a certain extent, but it doesn't explain. So this is a wrong the model is wrong. Okay? You cannot explain dark matter using this, but you roughly get the cushion at least that the velocity of the stars do not obey Newton's law. We know all of it, all the introductory physics works there, and you should all be able to address that. Read it up a little. I went a little fast because the time was already up. I'll talk about that kind of think about it. Oh, extra credit, right? Solve, yeah, extra credit. Yeah, Burden says solve the dark matter problem. Yeah, extra. So the extra credit question is solve the dark matter problem. That's a joke, yeah. But let's say dark matter problem. Yeah. Read up dark matter. Thank you. That's very less equations. So I like it.
Pictures.
Yeah. Was it clear, roughly? Clear? What I talked about? And hopefully you can think about it and come back to me next time.